Welcome, everyone, to the final session of this conference. Thanks to you all for sticking with us all day. The session is on blockchain programming languages and smart contracts. We have 3 speakers, the first of whom is Russell O'Connor from Blockstream, who is going to talk to us today about simplicity. So I will hand off to Russell.
All right. Thank you, Andrew. So simplicity is a programming language that I've been working on at Blockstream. I call it sort of an alternative or reimagination of Bitcoin script as it would have been if I had invented Bitcoin. Sort of an alternative or a new instruction set that is compatible with Bitcoin. It could be soft forked in, and we would experiment it with it on side chains such as Elements or Liquid. But first, I think I should reflect a little bit on the Bitcoin script, so when I first got interested in Bitcoin, I was very intrigued by this idea of programmable money, and because it had this little programming language called Bitcoin script that you could program with. But Bitcoin script has some problems, and I think it's fair to say that Bitcoin script in many ways failed to achieve its sort of design goals the way it was implemented. To get a little bit technical for those people who are familiar with Bitcoin script, when you create a transaction in Bitcoin that you want to redeem, right? There's 2 components to the script. The script pub key gets put into the UTXO, and then when you spend it, you have this script sig, and it has this really cool idea where you just concatenate the 2 scripts together and you execute it, and it looks really beautiful, and it was full of problems, right? Op return being the most severe thing where you can just bypass the entire signature verification process entirely. And it's sort of because this cool little symmetry idea it just doesn't actually work very well. Because there's this asymmetry actually between the commitment time when you have to put all your logical conditions and spending time. At spending time, you can just execute that spending portion of your script sig and produce its environment that the script pub key runs in explicitly, which is why today in Bitcoin, the script pub key is basically reduced to push operations only because that constructs the environment that the script pub key gets run in. And there were also many other problems with Bitcoin script. By the time I showed up on the scene, many of the opcodes had been disabled by Satoshi, including things like multiplication of numbers, right? So it had really been reduced to sort of this miniature script core that just lets you do digital signature verification and hash preimages. And even the time lock mechanism that was originally proposed was broken and had to have soft forks to enable it so that you could do something like that. So I've been for a long time thinking about, how can we achieve sort of the original design ideas of programmable money? And despite all my criticism for Bitcoin script, it was also incredibly innovative, I think. There were many, many good design features about Bitcoin script, including the fact that it has no loops, which makes it easy to do static analysis and understand the resource costs up front before you execute it, and the entire UTXO system, which I'll maybe talk a little bit more later. So I was thinking about designing, if we wanted to do something, what would we do if we were designing from the bottom up? Just forget about Bitcoin script and doing something else, right? So we want an expressive language that would allow you to create any sort of functionality you want, right? So maybe not have such a limited set of hash functions or cryptographic primitives. Maybe you want to get into elliptic curve primitive operations so you can do more fancy cryptographic protocols. And we'd also want something that's easy to reason about, something with simple and machine understandable semantics, so that we don't have semantics like in the original op left shift, where the semantics are, in some cases, your machine crashes. And the language that we're designing for a blockchain is very different from your traditional programming language, right? Because we're operating in an adversarial environment, right? So we want to be able to safely execute the resources, programs that you're receiving from basically the internet, right? So you want to be resistant to denial of service attacks. And this is very different from traditional programming languages where you're assumed to be cooperating with the compiler rather than being an adversary of the compiler, right? So different considerations have to be made. Also, blockchain languages are the form where you potentially are guarding hundreds of millions of dollars with a program that you expect to be executed once, right? So there's a very different sort of cost-benefit trade-off compared to traditional programming languages where you expect to run the program many times, and maybe you can uncover bugs that way, and maybe you don't have hundreds of millions of dollars at stake, And so another design feature is that I'd like a concise representation. This is something I talked about very early on, about reducing transportation costs through sharing and pruning of sub-expressions, right? Because any code that ends up not being executed in this one time that you execute your program, that doesn't actually have to be put on the blockchain because it never gets executed, right? So this is where the Merkleized abstract syntax tree masked sort of idea comes from. So simplicity is designed to be an extensible low-level, and I want to emphasize low-level programming language that has access to a wide range of intrinsic functions. So you would have direct access to elliptic curve operations, right? Schnorr signatures wouldn't require a soft fork if Bitcoin were designed this way because you would have access to the elliptic curve math to implement Schnorr signatures directly, right? Simplicity has features like transaction introspection, and in particular output introspection, which implies this covenant feature, which allows you to so Bitcoin script allows you to put conditions on who can spend it, whoever has access to the pub key. With the recent, not so recent soft forks, we have access to when it can be spent through the various time lock mechanisms, and the covenants tells you where it can be spent, basically, so a third feature. It also allows for delegation, which allows users to add sort of post hoc spending conditions after the UTXO has been committed, but before it's being redeemed. And the Merkleized abstract syntax that I talked about before allows you to prune away unused branches. So I only put this slide up here to make things concrete, right? This is the core computational part of the simplicity language. It's only 9 combinators. Every simplicity expression is a function, right, from some type formed out of disjoint union types and product types to, again, some type formed out of disjoint union types and product types. It's first order. There are no higher order functions, right? And this is like very, very low level and very simple and very generic. And from these 9 combinators, you can basically produce any computable function at all. And so this is the syntax of the simplicity core language. There's that does the computation, and the transaction introspection commands are extra sort of blockchain-specific combinators that go in addition to this core computational language. And so that will give you access to the transaction data to read from and produce Sighashes. This is the formal functional semantics of the simplicity language. And I don't expect you to read this necessarily, but the idea is that it's very short, and I made this joke about fitting it on a t-shirt before, and so now I have to go around with my t-shirt on, showing that that in fact is true. The design of simplicity is intended so that it's very, very hard to get the implementation a little wrong, right? So hopefully either it will be your implementation of the language will be correct, or it'll be so wrong that it won't even come close to working correctly, right? So we want to reduce these corner cases and remove subtle bugs from the implementation. And this is important for consensus because the interpreter of this language is consensus critical, and we want to make those components as simple as possible. And so that's why the name simplicity, right? But when you make the language simple, what you do is offload all the complexity onto the developer of the programmer, right? But I think that's the correct trade-off when it comes to consensus versus non-consensus critical components. So this is an example of how to implement a half adder for those who took digital logic at university, right? We have 2 input bits. and it produces a 2-output answer, which is the sum of the 2 input bits. And we don't have to go over the code, right? But the hand-wavy explanation here does a case analysis on the first bit. If the first bit is 0, then it produces an output which is 0 followed by a copy of the second bit. And the first bit is 1, then it produces 2-bit outputs where the first bit is a copy of the second bit, and the second bit is the inverse of the second bit. And then it becomes a mathematical theorem that what I just said about manipulating bits is, in fact, a description of the addition of two binary single-bit numbers. And because we have formal semantics, that's something you can prove. In Haskell, you can write it sort of this way. This is the sort of domain-specific language I use to generate simplicity expressions. But it gets compiled down to a concise sort of binary format. This is something you would transport over the network for your simplicity program. And when your node receives a simplicity program over the network, it reconstructs an internal memory representation of that simplicity expression as a DAG. And we can see some of the sharing that's going on here, right? Some of the nodes refer to the same sub-expression. And this sub-expression sharing allows us to make very sophisticated programs, but keeping them very concise. So this is the half adder written in sort of the DAG representation in memory. A full adder is composed of 2 half adders, but we can share that half adder sub-expression, and then we can build an 8-bit adder out of a bunch of full-bit adders. And then we can build the SHA-256 compression function, right? And we just keep on going, and we can build the Schnorr signature verification function, all out of these 9 combinators. Now you might think that this produces a very large program, and it sort of does, right? But computer science and programming is even more modular than you might think, right? So the full Schnorr signature verification program written in simplicity, which includes SHA-256 compression, because that's part of the protocol for Schnorr signature verification, right? That only amounts to about 7,000 nodes in the DAG, right? Because we have all that sharing that reuses various subroutines. And if it weren't for the sharing, it would be, if you unshared everything, it would end up being 6 trillion nodes, right? So we get this super exponential compression when you have sharing of sub-expressions. So it actually turns out really nice. To implement the simplicity language, we define this abstract machine that I call the bit machine. And the bit machine is basically a specialized abstract machine designed for interpreting or evaluating simplicity programs, right? So all those data values, they're encoded as bit strings. And we have this nice, cute little encoding so that substructures of your data structures are encoded so that those substructures are actually substrings of that data value, which allows the bit machine to very easily dive into the substructures. The bit machine sort of manipulates these 2 stacks of data while traversing this DAG that we saw over here. And it's got this sort of read data stack, this data stack that it reads from, and this other data stack that it writes to. And the nice thing, the most important aspect of the bit machine is that it provides operational semantics, right? So the denotational semantics tells you what the program does, and the operational semantics tells you what are the costs associated with evaluation. So we need to model these costs, and we can use the bit machine to model the costs. And modeling the costs is important when it comes to preventing denial of service attacks against your node, right? So we get a formal model of computational costs. We have a formal proof that I'll talk to you about that these operational semantics defined by the bit machine matches the denotational functional semantics I showed you earlier. And we can formally prove various static analysis of Bitcoin programs, in fact, can correctly compute costs in time and costs in space of how much time and space, how much memory will be used by the evaluator. Right. So jets are an important aspect of the design here that without it, we would run into the problem that if we try to interpret Schnorr signature verification just by interpreting simplicity, it would be still far too expensive. Even though it runs pretty fast, it runs in like a few minutes, right? But what we do is that because we have this Merkleized abstract syntax, we can recognize common sub-expressions, and then we can modify the interpreter as an sort of an optimization step to say, aha, I'm about to perform a Schnorr signature verification. So instead of running the simplicity interpreter, what we're going to do is we're going to call into libsecp and run this Schnorr signature verification through there and come back, right? This doesn't change the semantics of the language, right? But it does bring the operational costs down to a respectable level. So we need to specify these, the behavior of the jets, and the very cheap solution to specifying behavior of jets is just to simply specify them by writing them in simplicity. So this removes any ambiguity that we have about, so different implementations can agree on what the definition of these jets are. So in the worst case, when somebody implements it wrong, we can determine who's wrong because we have a formal specification. And in the best case, what we can do is use formal methods to prove that our implementation in C, in fact, correctly implements the jet. And we have some work done on that line, at least for the SHA-256 compression function already. So my opinion is the more jets, the better. We should have arithmetic. We should have elliptic curve operations. We should have all sorts of hash functions, digital signature verification. Anything reasonable that we would want, we should make a jet. So one of the goals here is high assurance. That's part of what we're talking about here today. So we want to use software proof assistance to specify semantics and reason about simplicity expressions, not only for jets, but also for the programs that people develop. Because if you're going to secure $100 million worth of value by one of these programs, maybe it's worth spending a few $100,000 or tens of thousands of dollars to verify it. It might be a good return on investment. So I use the Coq proof assistant, but simplicity semantics are simple enough that you could probably define it in basically any popular software proof assistant. So we have a verification of the SHA-256 compression function that's been developed in simplicity. We basically take the specification of SHA-256 from Princeton's verifiable C project, where they did where they verified OpenSSL's implementation of SHA-256. So we grabbed that specification, proved that the simplicity program produces the same result as. And basically, we get a net result that we have a formal proof checked in Coq that the simplicity program produces the same output that the OpenSSL implementation of SHA-256 produces. And that means that we can safely use the C interpreter to call into OpenSSL's implementation of SHA-256. And we know that we are not going to change the semantics that way. And the idea would be to do this for all the various jets that we want to implement. In addition to that, having a formal specification of simplicity is great on one hand, right? But when you implement it in C, and C becomes your consensus implementation, then if your C code doesn't match the formal description I've given of simplicity, then turns out your consensus critical C code is the actual definition of what you're doing, not whatever I put on a bunch of slides or on a T-shirt. So our proposed solution there is to use, again, the verifiable C component of the verified software tool chain that's being developed at Princeton. And I'd like to verify the C implementation of the simplicity interpreter by proving it matches the Coq semantics that define the Coq language. And then we'll have a very, very great story to tell about the correctness all the way from the implementation to the interpreter, to the definition of the simplicity language, to the programs that people write in simplicity. We can prove that those are going to be, in fact, correctly executed by the C interpreter. Simplicity has a lot of applications. So the way it's going to be deployed is that right now I have just built sort of a branch off the Elements project. Elements is a sidechain developed by Blockstream based on Bitcoin Core code. And now there's a branch there where the simplicity interpreter has been integrated, and you can actually send reg test funds to a simplicity contract and redeem them. That's very recent stuff. And then hopefully this will get deployed after some more vetting and various other completed work into the Liquid sidechain and maybe other sidechains where we can experiment with it. And you can actually build very interesting applications with simplicity. For instance, the vault construct, where you want to do this want to force a two-phase withdrawal of funds that are protected. So the way it works is that you have this first phase of withdrawal that goes onto the blockchain, and then you're forced into some 24-hour or maybe week-long time delay before sending it on to the ultimate destination. And during that delay period, you have this cancellation clause that you can sort of invoke to recover the funds. And that way, the idea is that to enforce that if your wallet, your hot wallet private key is stolen, they have to post, in order to steal the funds, they have to post it on the blockchain, and then they have to go through this week delay, which you can detect, and then pull out some sort of recovery key from cold storage to recover it. Simplicity can be used for transaction rebinding. This is part under consideration for Lightning's new L2 protocol. Could be you wouldn't need to add any soft forks. It would just work with simplicity. You can add velocity limits to hot wallets using covenants to check the time delays on your spending transaction and then limit the number of the amount you're spending to be proportional to the time period. We can do, again, delegation of UTXOs, right? So you can delegate to your administrator when you're going on vacation control of your UTXO funds, all without going on chain. And then you can even add to that side conditions to those delegations, right? So you can add limits on the number of funds that you delegate or some velocity limit on that delegation you give to your administrator. We could do sort of escrow for digitally signed proof of delivery, right? So if UPS produces some sort of certificate saying that they delivered something, you could automatically release things under those conditions. That's sort of this Oracle model where you use an Oracle to connect the real world to the blockchain, right? For multi-asset sidechains like we have in Liquid, right, we can do automatic partial order fills, right? So it's fairly easy to do sort of an order with a transaction in Liquid, right? But if that order is going to be partially filled, that's a little bit more difficult. It requires a lot of interaction between the two participants to come up with subset of the transaction. They all have to be online at the same time to sign things. But you can create a smart contract with simplicity that's familiar with the ratio of the two assets that you're requesting. And then when somebody comes along, they can just partially fulfill the transaction, and the remainder balance is automatically respent using a covenant mechanism back to the same script or the same simplicity expression in order to be posted for other people to fulfill the remainder of your trade that you're trying to do. But the most important simplicity application is the ones that I haven't thought of, right? And so that's where you guys come in, is to find new and novel uses, because the idea behind simplicity is to provide that flexibility for people to design applications that I haven't even thought of, and to enable those constructions. One idea that I like here is this. We spent on the Bitcoin mailing list, there's been recent discussions about new Sighash formats and stuff like that. Simplicity enables what I call universal Sighash, right? So this is a combination of delegation with introspection, where basically you can specify any hash of the transaction data that you want and sign for that, right? So if you want to only do the outputs or some subset of the outputs or some subset of the inputs of the outputs, at signing time you can decide which subset you're going to do. So you provide, using the delegation mechanism, a simplicity expression that constructs the particular aspects of the transaction that you want to hash together, and then you sign the Merkle root of the simplicity expression that generates it. That's signing the Sighash plus signing the message hash as well. So this is my call to action, right? In my implementation, there's much consensus critical work to be done, mostly about enabling limitations on and preventing various denial of service attacks that haven't been implemented yet. But if you're interested in using simplicity to experiment with, and you're not planning to DOS yourself, then this is something that you can actually start working on basically starting today. So are you a researcher that's doing novel smart contracts based on UTXO smart contracts, but you need sort of computation that's not available in Bitcoin, right? So now you can use simplicity. Some UTX-based model is actually very interesting. It has some advantages and disadvantages, right? Some people will say, well, you don't have disadvantages. You don't have concurrent access to a global state, which is too bad. But it has some advantages as well. For instance, there's no access to global mutable state. And it actually also has this, so that makes things way more simple to reason about. And UTXO-based systems has this automatic ability so that when you have sort of multiple concurrent solutions to UTXO, you're guaranteed that at most one will ever get committed to the blockchain. And so that's very convenient, right? So do you need novel cryptographic primitives to work with? Are you working with blinded values? Do you need pairing-based crypto? We can add jets for that. Are you interested in making tooling so we can, because simplicity is a low-level language. It's like writing in assembly. I expect multiple higher-level languages be compiled to simplicity. And are you interested in doing formal verifications of protocols, of specifications of implementations, and stuff like that? There's lots of work that could be done here. And in closing, I want to mention, although simplicity is designed for this blockchain application, simplicity's expression turns out to be basically the same class as that of a Boolean circuit, right? And so, for instance, a Boolean circuit is actually just a special case of our arithmetic circuit. And if you've gone to some of the talks here, what we can do is we can generate from simplicity expressions a set of quadratic polynomial constraints that basically evaluate the simplicity program as a sort of algebraic constraint system. And this is useful for various zero-knowledge proof systems like bulletproofs and a whole host of other things, right? So there could be some reuse here of taking verified simplicity expressions to generate various succinct cryptographic proofs, right? So where can you get more information? There's an introduction PDF link over here. We have a GitHub repository with code in the technical report and this prototype integration into the Elements sidechain. All right. Don't trust, verify. Thank you.
It looked like this is sort of like a first-order fragment of the simply typed lambda calculus characterization.
Yeah, that's a fair characterization. I mean, it's more related to the sequent calculus than the lambda calculus, okay, right? But those things are, of course, closely connected to each other.
Sure. Okay. And then you're primarily targeting this as a low-level language that people will compile to rather than something that people will write in, right?
That's correct.
All right. Thank you.
And Matt?
I have a question that might make you go home and cry. So obviously using a verified toolchain is much better, but have you looked at all at, assuming we're going to use Clang and LLVM to compile the rest of the consensus critical source code, have you looked at kind of taking simplicity expressions and just converting them to LLVM IR as a way to much more cheaply create jets under the same, let's say, trust model of a compiler behaving correctly?
Right. I haven't looked into that. I think that is an entirely reasonable aspect to research, but my time is limited. So if somebody else wants to do that, I think that'd be a great thing to investigate.
OK. I have a question. So you mentioned you have a fork or a branch of the Elements project where we can use simplicity. You can send coins to simplicity programs and spend. What tooling exists to generate these programs in the first place? Right.
So at the moment, the simplicity programs are generated by some poorly documented Haskell code that's in the main simplicity repository. But there's really no tooling to integrate it with the Elements with the transactions, right? So the way I've done it is basically hand editing hex, right? But I think that can be very quickly filled with tooling, especially interested and motivated parties who might be interested in using the Elements to vet their new idea.
Awesome.
Hey, I have a question. How does simplicity relate to the idea of script pub key and script sig? Like, is the program the script pub key and then the script sig is an input?
Yeah, so it's automatically combines sort of the pay to script hash idea into a single construct, right? So what you do is you use this Merkleized abstract syntax tree to compute the Merkle root of your simplicity expression, and that's equivalent to that's sort of the equivalent of the script public key. That's what you put in your address that you send to, right? So it's very concise. And then during redemption, what you do is you provide the program. This is where the pay to script hash kind of works, right? You provide the simplicity program, and then as part of the consensus rules, you have to recompute the commitment Merkle root of that program to make sure it matches. And then there's some other witness data that's hanging on the leaves of that program that is malleable. This corresponds to script sig, which is not included in that commitment Merkle root calculation, but is committed as part of the witness data.
Thanks.
Great. We don't have time for any more questions, so let's thank Russell again.